You're holding your phone right now. Maybe you're in bed, maybe on the toilet. I don't judge. But that little rectangle in your hand is making billions of decisions every single second. Billions, and it's all happening because of something so simple, so beautifully stupid, that when I tell you how it works, you're going to feel like you've been lied to your whole life. Tonight we're diving into how computers think, a gentle journey through logic gates and processing. Forget everything Hollywood told you about artificial intelligence and robot uprisings. This is the real story, and trust me, it's somehow both more boring and more mind-blowing than you could possibly imagine. So before you get too comfortable, hit that like button if you enjoy having your brain gently scrambled, and let me know in the comments what device you're watching this on. Now, dim the lights, maybe grab something stronger than coffee, and let's jump in. You wake up. It's 1946. You're standing in a room the size of a gymnasium at the University of Pennsylvania. The air smells like hot metal and burning dust, that specific scent of overheated electronics that anyone who's fried a graphics card knows too well. Before you stands ENIAC, the electronic numerical integrator and computer, 30 tons of pure, unadulterated computational beef, 18,000 vacuum tubes glowing like a city skyline, each one a potential point of failure. The heat coming off this thing could roast a turkey. The sound. Imagine 10,000 angry wasps trapped in a metal box. This is what thinking looked like before anyone really understood what thinking was. The scientists in white coats are scrambling around, replacing tubes that burn out every few minutes. One of them, a woman named Betty Holberton, looks up from her clipboard and catches your eye. She's one of 6 women who actually programmed this beast, though history will conveniently forget to mention that for about 50 years. She walks over, sweat beading on her forehead from the oppressive heat. You know what this thing is doing right now? She asks. Multiplying, just multiplying 2 numbers. It's been at it for 3 minutes. Your phone could do the same calculation about 1 billion times in the time it took me to say that sentence. But here's the kicker. The fundamental way your phone thinks, the basic logical operations it uses, they're exactly the same as what ENIAC is doing right now. We just got really good at making them tiny. And I mean stupid tiny. The transistors in your phone are about 14 nanometers wide. That's 14 billionths of a meter. To put that in perspective, if a transistor was the size of a house, an actual house would be the size of Earth, not a country, the entire planet. Betty hands you a vacuum tube. It's warm, almost uncomfortably so, and you can see the delicate filament glowing orange inside. This, she says, is a switch. That's it, a switch that can be controlled by electricity instead of your finger. When current flows through it, it's on. When it doesn't, it's off. 1 or 0, true or false, yes or no. Every single thing a computer has ever done, from calculating missile trajectories to rendering your ex's Instagram stories, comes down to combinations of these simple decisions. You're about to ask her how something so simple could possibly do math when one of the tubes explodes. Not a little pop. A proper explosion. Glass shards scatter across the floor like deadly confetti. The smell of ozone fills your nostrils. 2 technicians rush over with a replacement, stepping carefully through the minefield of broken glass. This happens about once every 7 minutes. Betty mentions casually, pulling a shard from her hair. We keep a team of people just to replace tubes. It's like trying to do brain surgery while the brain keeps catching fire. She leads you to a massive panel covered in cables. Each cable is about as thick as your thumb, and there are thousands of them, creating a waterfall of black rubber that looks like something HR Geiger would design if he was really into office supplies. This is the program, she explains. We physically rewire the machine for every new problem. Want to calculate a different trajectory? That's 3 days of rewiring. Want to add instead of multiply? Better clear your weekend. You reach out to touch one of the cables and immediately pull your hand back. It's scorching hot. Everything here is hot. The room temperature is pushing 95 degrees Fahrenheit, and that's with industrial fans running constantly. The noise is overwhelming. Beyond the wasp hum of the tubes, there's the clacking of relays, the whir of fans, and the occasional profanity from a technician who just burned themselves. This is the birthplace of the digital age, and it's about as pleasant as standing inside a running dishwasher. Betty shows you a calculation ENNIS just completed. It's a ballistic trajectory, the path a shell takes when fired from a cannon. Before ENIS, a team of human computers, mostly women with mathematics degrees, would take about 40 hours to calculate one trajectory. ENIS just did it in 30 seconds. Of course, it took 2 weeks to program it to do that calculation, but hey, progress is progress. You want to know the really insane part? Betty leans in conspiratorially. We don't actually know how to make it think. We just know how to make it calculate. There's a difference, but nobody's quite figured out what it is yet. The lights flicker. Another tube just died somewhere in ENIAC's massive bulk. Betty doesn't even look up anymore. She's explaining how these switches, these tubes, can somehow add 2 plus 2 and get 4. It starts with logic gates, she says, drawing on a dusty chalkboard. The chalk squeaks, adding another layer to the cacophony. A gate is just a combination of switches that makes a decision. She draws 2 switches in a row. This is an AND gate. Both switches need to be on for current to flow through. Both conditions must be true. Like saying you need your keys and your car to drive. Simple, right? Then she draws 2 switches in parallel. This is an OR gate. Current flows if either switch is on. You can watch Netflix on your phone or your laptop. Still with me? You nod though the heat is making your head swim. The air tastes metallic now, like licking a battery. She continues, her chalk flying across the board. Now here's where it gets fun. She draws a configuration that makes your brain itch. This is an XOR gate. Exclusive OR current flows if one switch is on, but not if both are, like a light controlled by 2 switches in your hallway. Flip either one to change the state. This pattern, this specific arrangement of possibilities, is the heartbeat of every digital device you'll ever touch. But you don't know that yet. In 1946, you're just trying not to pass out from the heat. You're watching Betty explain how combinations of these gates can add binary numbers, each calculation rippling through the machine, like dominoes falling in slow motion. Except some dominoes randomly explode, and you have to reset that part of the chain. A technician runs past carrying a box of fresh vacuum tubes. His shirt is soaked through with sweat. The concrete floor is stained with rings of coffee and darker patches where tubes have exploded and burned. This is the glamorous world of computing that nobody talks about. The part where brilliant minds spent their days essentially babysitting a temperamental giant baby made of glass and metal. Betty finishes her explanation and looks at you expectantly. You realize she's just shown you how to build addition from nothing but switches. Not program addition, but build it from the pure logic of electricity flowing or not flowing. Your mind reels at the implications. If you can add, you can subtract. If you can add and subtract, you can multiply and divide. If you can do arithmetic, you can do algebra. If you can do algebra, you can do calculus. If you can do calculus, you can model physics. If you can model physics, you can simulate reality. all from switches, on or off, 1 or 0. The foundation of everything from your alarm clock to artificial intelligence, built on the simplest decision possible. Be electricity or don't. Comment below if your brain is starting to melt, because we're just getting started. We haven't even talked about how these switches learn to remember things yet. Let's jump forward. It's 1958. You're in a laboratory at Texas Instruments, and a man named Jack Kilby is about to show you something that will make ENIAC look like a stone tablet. The room doesn't smell like burning metal anymore. It smells like chemicals, sharp and acidic. The kind of smell that makes you very aware of your mucous membranes. Kilby holds up something so small you have to squint to see it properly. It's a piece of germanium, a semiconducting element about the size of a paperclip. Embedded in it are all the components of an electronic circuit, not connected by wires, not soldered together, built into the very structure of the material itself. This is the first integrated circuit, and it's uglier than a mudskipper's family reunion. Wires stick out at weird angles like a spider that got stepped on. It looks like something a kid would make in shop class and get a C- for effort. But this ugly little bug is about to change everything. You see, Kilby explains, adjusting his thick-rimmed glasses, the problem with ENIAC wasn't the logic. The logic was sound. The problem was the tyranny of numbers. Too many components, too many connections, too many points of failure. Every wire was a potential problem. Every solder joint a future headache. What if, he continues, getting excited now, instead of connecting components, we just carved them into a single piece of material? No wires to break, no connections to fail, just pure solid-state logic. He powers up the circuit. Nothing explodes. Nothing even gets particularly warm. It just quietly does its job, oscillating at a steady frequency, proving that you can build electronic circuits inside a semiconductor. The implications hit you like a freight train made of mathematics. If you can put one circuit on a chip, you can put two. If you can put two, you can put four. If you can put four, well, nobody knows where it ends. Kilby certainly doesn't. When asked how many components might eventually fit on a single chip, he guesses maybe a dozen, maybe 2 dozen if they get really clever about it. Your smartphone has about 10 billion transistors. Kilby undershot by approximately 10 billion. But here's the beautiful part. Those 10 billion transistors, they're all doing the same thing those vacuum tubes were doing. On or off, 1 or 0, just very, very, very small, and very, very, very fast. We're talking about switches that can flip billions of times per second. That's billion with a B. In the time it takes you to blink, your computer has made more decisions than every human who has ever lived has made in their entire collective existence. Kilby's assistant walks in with a tray of similar circuits, each one a slight variation, each one a failed experiment. You pick one up. It's surprisingly heavy for its size, dense like a piece of jewelry. The germanium has a strange metallic sheen, not quite silver, not quite grey, like looking at mercury under glass. This one, the assistant says, failed because we couldn't control the doping properly. Doping. That's what they call it when they add impurities to the semiconductor. Specific atoms in specific places to create regions that either have extra electrons, N-type, or missing electrons, P-type. The boundaries between these regions are where the magic happens. That's where you get your switches, your transistors, built into the very atomic structure of the material. You want to understand how a transistor works? Kilby asks. Imagine you're at a nightclub. There's a bouncer at the door. That's your transistor gate. When you apply voltage to the gate, you're essentially slipping the bouncer a 20. Suddenly current can flow from source to drain. People can get into the club. Remove the voltage. The bouncer goes back to crossing his arms, and nobody's getting in. Simple as that, except instead of people, we're talking about electrons, and instead of a nightclub, we're talking about, well, actually, the nightclub analogy works pretty well. Electrons want to party in the conduction band. The assistant pulls out a microscope. Not an electron microscope. Those don't exist yet. Just a really good optical one. He puts one of the circuits under it and lets you look. What you see looks like an alien city. Geometric patterns etched into the germanium. Traces of metal creating highways for electrons to travel. It's beautiful in a cold mathematical way, like looking at the blueprints for reality itself. But here's what's really going to bake your noodle, Kilby says. We can make these circuits do memory. You pull back from the microscope. Memory? Like remembering things. Exactly. Watch this. He connects two transistors in a specific configuration, their outputs feeding back into each other's inputs. It's like two people in an argument where each one's position depends on disagreeing with the other. If one says yes, the other says no, which makes the first one continue saying yes, which makes the second continue saying no, forever and ever until you forcibly change one of their minds. This is called a flip-flop, he explains. Once you set it to 1 or 0, it stays that way. It remembers. One bit of information, stored indefinitely, or at least until the power goes out. Your phone has billions of these, holding everything from your photos to your poor decision-making history at 2 a.m. The room suddenly feels very small. You're looking at the birth of digital memory, and it's just two transistors arguing with each other like an old married couple. The assistant brings over another device. This one's different. Instead of germanium, it's made of silicon. Cheaper, he explains. More abundant. Sand is basically just silicon dioxide. We're literally making thinking machines out of fancy sand. This particular chip has 4 flip-flops on it. 4 whole bits of memory. You could store a number from 0 to 15. Kilby's team is very proud of this. In your time, a typical photo on your phone uses about 40 million bits. But in 1958, 4 bits feels like conquering Everest. The really clever bit, Kilby continues, and you can tell he's been waiting to show this off, is that we can make these flip-flops work together. He starts connecting them in a chain. Each flip-flop's output connects to the next one's input. When you send a pulse, the pattern shifts down the line, like a conga line of electrons, each one remembering what the one before it was doing. This is a shift register, he announces. We can move data around inside the chip, not just store it, but manipulate it, shuffle it, process it. Suddenly you see it. The whole picture clicks into place. Logic gates to make decisions. Flip-flops to remember things. Shift registers to move information around. You can build anything with these. A calculator, a computer, a phone that fits in your pocket and has access to all human knowledge, and you use it to watch cats falling off things. But Kilby doesn't see that far ahead. He's worried about more immediate problems, like how to actually manufacture these things reliably. Right now, about 90% of the chips they make don't work. They're too sensitive to contamination. A single speck of dust, a fingerprint, even breathing on them wrong, can ruin the circuit. The clean rooms of the future, where people dress like they're about to perform surgery on an alien, don't exist yet. They're making these things in a room that's barely cleaner than your average kitchen. One of the lab techs actually smokes while working. In 20 years, Kilby muses, we might be able to put 1,000 transistors on a single chip, maybe even 10,000 if we really push it. He has no idea that something called Moore's law is about to grab the semiconductor industry by the throat. and squeeze out exponential growth for the next 60 years. Gordon Moore won't even make his famous observation for another 7 years. Right now, it's just Kilby, his ugly little circuits, and a dream of making electronics smaller. Drop a comment if you're starting to see how we got from room-sized computers to pocket-sized supercomputers, because we're about to meet the man who figured out how to mass-produce these things, and his solution involves one of the most toxic substances known to humanity. It's 1968. You're standing in a clean room at Fairchild Semiconductor, except it's not really that clean by modern standards. People are wearing lab coats, sure, but that's about it. No bunny suits, no face masks, just regular clothes under a white coat like they're pretending to be doctors. The air has a different quality though. Filtered but not enough. You can still smell the photoresist chemicals, sweet and toxic, the kind of smell that definitely shouldn't be sweet, but is like antifreeze or certain deaths. Robert Noyce is here, co-founder of Fairchild and future co-founder of Intel, though he doesn't know that yet. He's about to show you the process that makes modern computing possible. The planner process. It sounds boring. It is boring. It's also the most important manufacturing innovation you've never heard of. He holds up a silicon wafer, about 2 inches across, polished to a mirror finish. You can see your reflection in it, distorted like a funhouse mirror. This starts as a cylinder of pure silicon, he explains. We slice it like salami, but thinner, much thinner, about 0.5 millimeter. Then we polish it until it's so flat that if you expanded it to the size of the Earth, the biggest mountain would be about 6 feet tall. The wafer goes into a furnace, not a regular furnace. This thing hits 2000 degrees Fahrenheit. The silicon oxidizes, growing a layer of glass on its surface, pure silicon dioxide. The same stuff that makes up quartz, but in a layer so thin you need special equipment to even confirm it exists. Now comes the fun part, Noyce says, and his definition of fun is clearly different from yours. They coat the wafer with photoresist, a chemical that changes properties when exposed to light. It's like the stuff in old-school film photography, but instead of capturing your awkward family photos, it's capturing circuit patterns. A technician wheels over what looks like a medieval torture device, had a baby with a projector. This is a photolithography machine. It shines ultraviolet light through a mask, a piece of glass with the circuit pattern printed on it in chrome. The pattern is projected onto the wafer, shrunk down by lenses. Everywhere the light hits, the photoresist changes, becomes either soluble or insoluble, depending on the type. They develop it like a photograph, washing away the exposed or unexposed areas, leaving behind a pattern of photoresist that matches the circuit design. Through the gaps in this pattern, they can add dopants, etch away oxide, deposit metal, build up the circuit layer by layer, like the world's most complex lasagna. A technician drops a wafer. It shatters like the world's most expensive cookie. Nobody even flinches. This happens all the time. The yield rate, the percentage of chips that actually work, is maybe 30% on a good day. Most of the wafer is garbage. They're literally throwing away more than they keep. But here's the thing. Noyce explains, picking up a fragment of the broken wafer. Even at 30% yield, we can make hundreds of circuits at once, all identical, all made in parallel. It doesn't take any longer to make 100 circuits than it does to make one. This is the revolution. Not making circuits smaller, though that's happening too. It's making them all at once, using photography and chemistry instead of soldering irons and steady hands. No more connecting components by hand. No more wiring mistakes, just light, chemicals, and silicon. He shows you a finished chip, still on the wafer, It's tiny, maybe a few millimeters square. Under a microscope, you can see the patterns. Metal traces running like rivers between rectangular transistors. It looks organic, almost alive, like looking at the neural pathways of some silicon-based life form. This one has about 100 transistors, Noyce says proudly. It's a simple logic circuit, can do basic arithmetic. In your pocket, your phone's processor has about 10 billion transistors, made using essentially the same process, just shrunk down to an absurd degree. The photolithography machines of your time cost more than private jets and are the size of school buses. But the basic idea, shine light through a mask, develop the pattern, process the exposed areas, repeat a few dozen times to build up all the layers. It's photography and chemistry pretending to be wizardry. A tech brings over a bottle of hydrofluoric acid. This is what we use to etch the oxide, he says casually. You step back. Hydrofluoric acid is nightmare fuel in liquid form. It passes through skin like it isn't there, dissolves bones, and you might not even feel it happening until it's too late. The tech is holding it like it's maple syrup. OSHA doesn't exist yet. The Clean Air Act is still 2 years away. The technicians here are basically marinating in chemicals that future generations will require hazmat suits to handle. One woman is pregnant and still working directly with the solvents. Nobody thinks this is unusual. This is the price of progress in 1968. Noyce walks you through the entire process, step by step. It takes about 2 weeks to go from blank wafer to finished chips. 2 weeks of heating, cooling, coating, exposing, developing, etching, doping, depositing. Each step has to be perfect. One speck of dust at the wrong moment and the chip is dead. One temperature fluctuation during doping and the transistors won't work. One misalignment of the mask and the layers don't connect properly. We're getting better at it. Noyce assures you, every year we can make the features a little smaller, pack a few more transistors in. There's no physical reason we can't keep shrinking things down. The atoms aren't going anywhere. You want to tell him that in 50 years, the features will be so small that quantum mechanics starts becoming a problem, that electrons will tunnel through barriers they're not supposed to, that engineers will spend billions of dollars fighting the fundamental uncertainty of reality itself. But you don't. He wouldn't believe you anyway. Right now, they're fighting more mundane problems, like how to connect the chip to the outside world. The transistors might be microscopic, but they still need to talk to the rest of the circuit. They use gold wires, thinner than human hair, ultrasonically welded to pads on the chip. A woman with steadier hands than a neurosurgeon does this under a microscope, one wire at a time. She can do about 100 chips a day. Her eyes are going to be shot by the time she's 40, but nobody's tracking that yet. The finished chips go into ceramic or plastic packages, sealed away from the world. The package is 1,000 times bigger than the actual chip, but it has to be. Human fingers can't handle something the size of a grain of sand, not without losing it in the carpet. Anyway, and trust me, you do not want to step on a bare chip. It's like stepping on a Lego, if the Lego was made of glass and cost a week's salary. Noyce shows you the testing station. Each chip gets probed with tiny needles, electricity flowing through to check every single transistor, every connection. Most fail. They get tossed into a bin that will eventually be processed to recover the gold. Even the failures are worth something. The ones that pass get a spot of paint, marking them as good. These will go into calculators, early computers, military equipment, each one a tiny piece of crystallized logic, a fragment of pure thought frozen in silicon. You realize you're watching the birth of an industry that will reshape the world more fundamentally than the steam engine or electricity. But right now, it's just people in a somewhat clean room, playing with light and chemicals, trying to make sand think. Hit that like button if you're amazed. We figured out how to mass-produce logic itself. Now it's 1971. You're at Intel, the company Noyce co-founded after leaving Fairchild. The building smells new, like fresh carpet and ambition. A young engineer named Ted Hoff wants to show you something that's about to flip the entire computer industry on its head. He holds up a chip. It doesn't look special. Same ceramic package as any other. But inside this package is something unprecedented. 4,000 transistors arranged not just to do one specific task, but to do any task you can program it for. This is the 4004, the world's first commercial microprocessor. Before this, Hoff explains, every calculator, every computer, every digital device needed custom chips designed for that specific purpose. A calculator chip could only calculate. A clock chip could only keep time. It was like having a different car for every possible destination. Insane, expensive, inflexible. But this chip is different. It's a general-purpose computing engine. It reads instructions from memory and executes them one by one. Same chip can be a calculator, a traffic light controller, or a cash register. Just change the instructions. You're looking at the birth of software as we know it. The 4004 can do about 90,000 operations per second. Your phone does about 3 trillion, but the principle is identical. Fetch instruction, decode what it means, execute it, store the result, repeat, over and over, billions of times per second, like a metronome made of electrons. Hoff shows you the instruction set. 46 different operations the chip can perform. Add, subtract, jump to a different part of the program, compare two numbers. Each instruction is a pattern of ones and zeros, a specific configuration that tells the chip what to do. You could literally program this thing by flipping switches to input binary code. People actually did this. They sat there, flipping switches for hours, entering programs one bit at a time, like texting with your television remote control, but worse. The chip itself is a maze of microscopic components. The arithmetic logic unit, which does the actual calculations, the register file, tiny patches of memory that hold numbers while they're being processed, the control unit, which orchestrates everything like a conductor who can only communicate in binary, and connecting it all. Buses, not the kind you ride, but highways for data, shuttling information between components at the speed of electricity. Each bus is multiple wires in parallel, letting the chip move entire bytes at once, instead of one bit at a time. It's parallel processing at the most fundamental level. Hoff boots up a demonstration system. It's not pretty. A mess of wires and breadboards that looks like someone sneezed on an electronics store. But when he flips the power switch, LEDs start blinking in patterns. The 4004 is running a program, counting from 0 to 15 over and over, displaying the result in binary on the LEDs. This might not seem impressive, but consider what's actually happening. The chip is reading instructions from memory, figuring out what they mean, performing the operation, and storing the result. It's thinking, in the most basic sense of the word, not consciousness, not intelligence, just pure mechanical thought, like a player piano that can rewrite its own music roll. He shows you the development system they use to write programs. It's the size of a refrigerator and costs more than a house. You write your program on paper first, Hoff explains, then convert it to machine code by hand. Then you punch it into paper tape or toggle it in through switches. If you made a mistake, you start over. There's no delete key, no undo, Just you, your brain, and the unforgiving nature of binary logic. A younger engineer named Federico Fagin walks over. He's the one who actually designed the chip's layout, figured out how to cram 4,000 transistors into a space smaller than your fingernail. He looks tired. The kind of tired that comes from staring at microscope images until your eyes forget how to focus on anything else. The hardest part, Fagin says, wasn't fitting everything in. It was making sure the signals arrived at the right time. Electricity might seem instantaneous, but it's not. It takes time for signals to propagate through the chip. Nanoseconds. But when you're trying to coordinate thousands of operations, those nanoseconds matter. He shows you timing diagrams, wavy lines that look like a seismograph, having a nervous breakdown. Each line represents a signal. When it goes high, when it goes low. The entire chip is a symphony of signals, all perfectly choreographed. One signal arrives too early or too late, and the whole thing falls apart. It's like conducting an orchestra, where the musicians are scattered across different continents, and the music travels at the speed of light. You have to account for every delay, every path the signal takes. The longer the wire, the longer the delay. It's maddening, but when it works, when all the signals align and the chip performs exactly as designed, it's beautiful. Pure logic made manifest in silicon and electricity. Fagin pulls out a wafer with dozens of 4004 chips on it. Most of them don't work. Little dots of ink mark the failures. The yield is getting better though, up to about 40%. Still throwing away more than half. But that's progress in this industry. Each working chip sells for $200. That's about $1,300 in your time's money, for something with the computing power of a musical greeting card. But companies are buying them as fast as Intel can make them. The potential is obvious. Instead of designing custom chips for every application, just use a microprocessor and change the software. It's like the difference between carving a new stamp for every letter versus using a printing press with movable type. Hoff shows you one of their customers' applications. A Japanese company called Busicom is using the 4004 in a calculator. The entire calculator program fits in 1024 bytes of memory. Your phone uses that much memory to store this sentence, but it works. Press a button, the processor reads the input, performs the calculation, displays the result. All those transistors dancing their binary ballet to figure out that 2 plus 2 equals 4. The real innovation, Hoff explains, isn't the processor itself, it's the idea of the processor. A universal machine that can become any machine through programming. It's the physical manifestation of something Alan Turing theorized in 1936. A device that can compute anything that is computable, given enough time and memory. You're looking at the ancestor of every CPU, GPU, and neural processing unit that will ever exist. They all trace their lineage back to this chip, this room, this moment when humanity figured out how to make a machine that could learn new tricks. An engineer in the corner is working on the next version, the 8008, 8-bit instead of 4-bit, meaning it can handle numbers up to 255 instead of just 15. The progression has begun: 4-bit, 8-bit, 16-bit, 32-bit, 64-bit. Each generation handling more data, running faster, consuming less power. Nobody in this room imagines that in 50 years kids will carry supercomputers in their pockets and use them primarily to share pictures of their lunch. They're just trying to make calculators cheaper. Sometimes revolutions happen by accident. The microprocessor wasn't meant to change the world. It was meant to save Busicom money on calculator chips. But once you create a universal computing machine, once you make software possible, you can't put that genie back in the bottle. Comment below what you think the engineers of 1971 would say if they saw what their invention became. Jump to 1977. You're in a garage in Los Altos, California. It smells like solder and stale pizza, with an undertone of body odor that suggests the two guys working here haven't seen sunlight in days. Steve Wozniak is hunched over a circuit board, meticulously placing components. Steve Jobs is on the phone, probably arguing with a supplier. This is where the Apple II is being born, though right now it looks more like a crime scene involving electronics. Wozniak looks up, his eyes red from strain. Want to see something cool? He doesn't wait for an answer. He powers up his latest creation. The screen, a modified television, flickers to life. Color appears, not just green on black like every other computer. Actual color, 8 whole colors, if you count black and white. In an industry where displaying text was considered an achievement, Woz has made a computer that can show pictures. The trick, he explains, pulling you over to look at the circuit board, is that I'm hijacking the TV's color system. Instead of generating proper color signals, I'm exploiting artifacts in how TVs interpret the signal. It's wrong, but it's wrong in exactly the right way. The board is a work of art, not aesthetically. It looks like someone tried to perform surgery on a robot, but the efficiency is breathtaking. Where other computers use dozens of chips, Woz has figured out how to do the same thing with a handful. He's not just an engineer, he's a minimalist poet working in silicon and copper. Look at this, he says, pointing to a particularly dense section of the board. This is the disk controller. Other companies use 40 chips for this. I did it with 8. How? They said it was impossible. I said they weren't trying hard enough. He's actually giddy about it. This is a man who gets genuinely excited about saving transistors the way other people get excited about sports scores. Jobs hangs up the phone and walks over. We need to talk about the case, he says. Woz rolls his eyes. Steve wants it to look like a kitchen appliance. Beige, friendly, not like a kit for electronics nerds. This starts an argument that apparently happens daily. Woz wants exposed circuits because they're beautiful. Jobs wants a closed case because normal humans are scared of circuit boards. They're both right, which makes the argument worse. The Apple II will eventually ship in a beige plastic case that looks like it belongs next to a toaster. It will sell millions. But right now in this garage, it's just exposed circuits and dreams. Woz shows you the memory map. This is where it gets really clever, he says. The way the computer organizes its memory is elegant in its simplicity. The first chunk is for the system, the next for your basic program, then screen memory, where each byte corresponds to a character or pixel on screen. Change a byte in screen memory, and the display updates instantly. It's like having a window directly into the computer's brain. You can literally watch it think by seeing the screen memory change. He writes a simple program, typing on a keyboard that looks like it was stolen from an electric typewriter, because it probably was. 10 print hello. 20 goto 10, the eternal greeting card of programming, an infinite loop of friendliness. But then he does something unexpected. He starts poking values directly into screen memory. Poke 10, 24, 65. The letter A appears in the corner of the screen. He's bypassing BASIC entirely, talking directly to the hardware. This is what separates a computer from a calculator. Woz explains, direct access to memory. You're not just running programs, you're reaching into the machine's guts and rearranging them. Every memory address is a lever you can pull, a switch you can flip. With great power comes great opportunity to crash everything. He demonstrates by poking a random value into a system memory location. The computer immediately freezes, cursor stuck mid-blink. Woz laughs and hits reset. Jobs comes back with a beer, even though it's 10 in the morning. We're going to democratize computing. He announces like he's declaring war. IBM thinks computers are for corporations. We're going to put them in homes. Schools everywhere. Woz snorts. Steve thinks he's changing the world. I just want to impress the Homebrew Computer Club. But they're both right. The Apple II will be the first computer that normal people can actually use. No soldering required. No understanding of hexadecimal necessary. Just plug it in and start typing. The power supply is another Wozniak masterpiece. Switching mode instead of linear, which means it's light, cool, and efficient. Other computers need fans. The Apple II runs silent. It's the difference between a jet engine and a whisper. Every detail has been obsessed over, thought about, optimized to the point of absurdity. A friend drops by with acoustic coupler modem. It's a box you literally place your phone handset into, and it converts audio tones to digital signals. 300 baud, meaning 300 bits per second. It would take about 3 hours to download a single photo from your phone's camera. But in 1977, it's magic. Woz connects it to the Apple II and dials into a bulletin board system. Text slowly scrolls across the screen, each character taking its sweet time to arrive. Someone in another city is typing a message about Star Wars which just came out. The future is happening in slow motion. This is the beginning of online culture. Woz says, people connecting their computers over phone lines, sharing programs, messages, ideas. Nobody quite knows what to do with it yet. But it's going to be huge. Jobs is less impressed. Who wants to wait 5 minutes to download a program you could buy at a store? He's missing the point entirely. It's not about efficiency, it's about connection. About computers talking to other computers, creating a network of intelligence that's greater than the sum of its parts. The friend leaves the modem. Woz immediately starts taking it apart to see how it works. This is his superpower. The ability to see a complex system and immediately understand how to simplify it. He's probably already figured out how to build a better modem with half the components. Jobs is back on the phone, arguing about plastic injection molding costs. The Apple II needs to be manufactured at scale, which means dealing with suppliers, factories, logistics. The garage startup phase is ending. Soon they'll need real offices, real employees, real business cards. But right now, it's just two Steves in a garage, building the future one solder joint at a time. The computer revolution isn't happening in some corporate laboratory or government facility. It's happening here, surrounded by empty pizza boxes and half-drunk beers, soundtracked by the buzz of fluorescent lights and the occasional profanity when someone burns themselves with a soldering iron. Woz shows you one more thing. A game he's been working on. A simple breakout clone. The paddle moves smoothly across the screen. The ball bounces with realistic physics. For 1977, it's incredible. The Apple II can do this because of how Woz designed the graphics system, with sprites and smooth animation in mind. It's not just a business machine pretending to play games. It's a game machine that happens to also do spreadsheets. This dual nature, serious and playful, will define personal computing for decades. Comment if you remember your first computer and what game you played on it. I bet it wasn't that different from what Woz is showing you right now. It's 1981. You're at IBM's headquarters in Boca Raton, Florida. The air conditioning is fighting a losing battle against the Florida humidity. The building smells like coffee, photocopier toner, and the particular desperation that comes from a massive corporation trying to be nimble. IBM, the company that practically invented corporate computing, is about to release something radical for them, a personal computer. Not radical in design. The IBM PC is about as exciting as a tax form. Beige box, green screen, keyboard that sounds like machine gun fire when you type, but radical in philosophy. For the first time, IBM is using off-the-shelf parts that anyone can buy. Don Estridge, the project leader, shows you around. His team has been working in secret, which at IBM is like trying to hide an elephant in a phone booth. We call it Project Chess, he says. 12 engineers 1 year build a computer that can compete with Apple. Except we're IBM. We don't compete, we dominate. The machine he shows you is solid, overbuilt. The keyboard alone weighs more than an entire modern laptop. Each key press feels like you're commanding something important to happen. The power supply could probably run a small refrigerator. This is a computer that means business, literally. But here's the revolutionary part. Estridge opens up the case. See these slots, expansion slots. Anyone can design a card to plug in here. Graphics, memory, networking, whatever. We're not locking people into our ecosystem. We're creating an open architecture. This decision will accidentally create the entire PC industry as you know it. Companies will clone the IBM PC, improve on it, make it cheaper. IBM will eventually exit the PC business entirely, but their architecture will live on in every non-Apple computer you'll ever use. The processor is an Intel 8088, a 16-bit chip pretending to be an 8-bit chip for compatibility reasons. It's like hiring a Ferrari to deliver pizza, technically capable of more, but constrained by the reality of the market. Memory is 64 kilobytes, expandable to 256 if you're rich. Your phone has about 60 million times more RAM, but in 1981, 64 kilobytes feels luxurious. You can run an entire operating system, a word processor, and still have room left over for your actual documents. A young programmer from Seattle is here, demonstrating his operating system. Bill Gates looks about 12 years old and has the social skills of someone who's spent too much time talking to computers. His company Microsoft has provided MS-DOS, the operating system for the IBM PC. Watch this, Gates says. Typing commands faster than you can follow. dir shows your files. copy duplicates them. dl deletes them. It's all text commands, no mouse, no graphics. You navigate your computer like you're having a conversation with a particularly literal-minded friend. The irony is that Gates bought the bones of MS-DOS from another company for $50,000 and modified it for IBM. He's about to become one of the richest humans in history based on software he didn't originally write. But he understood something IBM didn't. Hardware would become commodity, software would become king. Estridge shows you the BIOS chip, basic input-output system. This is the computer's most fundamental software, burned directly into read-only memory. When you turn on the PC, the BIOS runs first, checking memory, finding disk drives, making sure the computer isn't on fire. Then it hands control over to the operating system. It's like the computer's autonomic nervous system, handling all the functions you don't think about but would die without. The fascinating part is that the BIOS is copyrighted, but the architecture isn't. Other companies will reverse engineer this BIOS, creating clean room implementations that do the same thing without copying IBM's code. It's corporate espionage through legal loopholes. One company, Compaq, will hire programmers who've never seen IBM's code to recreate the BIOS based solely on observing what it does. Like reconstructing a recipe by tasting the cake, they'll succeed, and suddenly everyone can make IBM-compatible computers. An IBM executive walks by and sees Gates. He whispers something to Estridge about not letting the fox into the henhouse. He has no idea that the fox already owns the henhouse, the chickens, and the distribution rights to all future eggs. Microsoft's deal with IBM allows them to sell MS-DOS to other manufacturers. IBM thinks hardware is the product. Microsoft knows software is the real gold. The IBM PC costs about $3,000, which is $16,000 in your money. For that, you get a computer that can barely run a spreadsheet without sweating, but businesses are buying them faster than IBM can make them. Why? Because it says IBM on the front, and nobody ever got fired for buying IBM. Estridge shows you the manufacturing floor. It's nothing like the chaotic garage operations of Apple or the clean rooms of Intel. This is industrial efficiency. Computers rolling off assembly lines like Model T Fords, each one identical, tested, burned in for 48 hours to catch early failures. Quality control is everything. A failed Apple II is an angry customer. A failed IBM PC is a lawsuit from a Fortune 500 company. The testing process is brutal. Computers running in ovens. Computers being shaken until their teeth rattle. Computers having their power cycled thousands of times. If it's going to fail, IBM wants it to fail here, not on someone's desk. But the real genius of the IBM PC isn't the hardware or even the software. It's the documentation. IBM publishes complete technical specifications, circuit diagrams, BIOS source code listings. Everything you need to understand exactly how the PC works. It's like Ford publishing the blueprints to the Model T and saying, "Go ahead, make your own." This openness is partly strategic, partly accidental. IBM wants third parties to make expansion cards and software. They don't realize they're also enabling third parties to make entire computers. Within 2 years, there will be dozens of PC clones. Within 5 years, the clones will be better and cheaper than IBM's own machines. You pick up the technical reference manual. It's the size of a phone book and weighs about the same. Every circuit documented, every memory address explained. This is the Rosetta Stone of personal computing. Future engineers will study this manual like religious text, memorizing interrupt vectors and port addresses. The computer industry is about to explode, not because IBM made a great computer, but because they accidentally made a standard. They've created a recipe that anyone can follow, a blueprint for the digital age. The IBM PC isn't the best computer of 1981. The Apple II is more elegant. The Commodore VIC-20 is cheaper. The Xerox Star has a graphical interface that makes MS-DOS look like cave paintings. But the IBM PC has IBM's name on it, and that changes everything. Drop a like if you've ever used MS-DOS or remember the satisfaction of getting autoexec.bat configured just right. It's 1984. You're at Apple's campus in Cupertino. The atmosphere is electric, like the moments before a thunderstorm. Everyone knows something big is about to happen. The Macintosh is about to launch, and Steve Jobs is in full reality distortion field mode. You're standing in a lab where engineers are putting final touches on the Mac. The air smells like hot plastic and nervous sweat. Unlike the Apple II's chaotic beauty or the IBM PC's corporate efficiency, the Mac is something else entirely. It's a computer that doesn't want you to know it's a computer. The case is all curves and friendliness, like a robot that went to therapy and came out well adjusted. Inside it's just as radical. The entire computer fits on a single board. No expansion slots, no user-serviceable parts. It's sealed tighter than a submarine. This goes against everything the industry believes. Computers are supposed to be expandable, hackable, accessible. The Mac is a black box with a smile. An engineer named Burrell Smith shows you the logic board. He's crammed an entire computer into a space smaller than a pizza box. The traces on the circuit board are so dense they look like a city map drawn by someone with OCD. Every millimeter is accounted for, every component justified. The processor is a Motorola 68000, a true 32-bit chip in an industry still fumbling with 16 bits. But here's the kicker. Most of that power goes to drawing pictures. The Mac has a graphical user interface, windows and icons instead of command lines. It's using more computational power to draw a trash can icon than most computers use to run entire programs. This is what drove me crazy. Smith confides, "We're using this incredibly powerful processor to move pixels around. It feels like using a Ferrari to deliver newspapers." But Steve insisted, the user experience is everything. People shouldn't have to think about the computer. You're watching the birth of modern user interface design. Every smartphone, tablet, and computer you'll use in the future traces its DNA back to decisions being made in this room. Should windows overlap? How many pixels should a button be? What happens when you drag a file? These aren't technical questions anymore. They're philosophical ones. Susan Carey walks over with a sketchbook. She's designing the icons and fonts for the Mac, turning abstract computer concepts into friendly pictures. A document looks like a piece of paper. A folder looks like, well, a folder. The trash can looks like a trash can. Revolutionary. My job, she explains, is to make the computer feel human, not anthropomorphic, but relatable. When you drag a file to the trash, it should feel like throwing away paper, not executing a delete command. She shows you her process. Graph paper, where each square represents a pixel. She's designing fonts pixel by pixel, making sure each letter is readable on the Mac's 512 by 342 pixel screen. That's fewer pixels than a single app icon on your phone, but she's making it work. The attention to detail is obsessive. The Chicago font used for menus is designed to be readable at small sizes without anti-aliasing. The proportional spacing in text makes documents look like they were actually typeset, not just displayed on a screen. This is desktop publishing being born, though nobody's calling it that yet. Jobs storms through, trail of stressed engineers in his wake. He stops at a prototype and starts critiquing the startup sound. It needs to be warmer, more welcoming, like a Tibetan temple bell, but digital. The engineer looks like he wants to die. How do you make a computer sound like enlightenment? But this is peak Jobs. Every detail matters because every detail is part of the experience. The Mac isn't just a tool. It's a statement about how humans and computers should interact. Friendly, not intimidating. Visual, not textual. Intuitive, not learned. It's the exact opposite of MS-DOS, which is probably the point. The mouse is another revelation. Developed at Xerox PARC, but perfected here. One button, because Jobs decided more would confuse people. The ball inside rolls against encoding wheels, translating physical movement into cursor movement. It's purely mechanical, no optical sensors yet, and it needs to be cleaned constantly. But it works. Point and click instead of typing commands. Grandmothers can use this. Children can use this. You don't need to memorize anything. The software is even more radical than the hardware. Andy Hertzfeld shows you the Finder, the Mac's file management system. Files appear as icons on a desktop. You can drag them around, put them in folders, throw them away. It's a spatial metaphor for information management. Your computer's memory becomes a place you can navigate rather than a list you have to pass. But making this work required incredible engineering. The Mac has 128 kilobytes of RAM. The operating system, the graphical interface, and your actual program all have to fit in less memory than a single email uses today. It's like building a mansion inside a closet. Every byte counts. We had to get creative, Hertzfeld explains. The window manager shares memory with applications. The menu bar is actually part of the system, not each program, saving precious kilobytes. We're compressing functionality like a bonsai tree. The QuickDraw graphics library is a masterpiece of optimization. It can draw circles, rectangles, and text faster than most computers can clear the screen. Bill Atkinson, who wrote it, figured out how to make the 68000 processor do things Motorola didn't even know it could do. He's exploiting undocumented features, pushing the chip beyond its specifications. The 3.5-inch floppy disk drive is another innovation. Higher capacity than the 5.25-inch floppies everyone else uses, but in a smaller, more durable package. The disk slides in with a satisfying car chunk. Auto-eject when you drag the disk icon to the trash, which is intuitive but also kind of weird when you think about it. Why would you throw away a disk to eject it? The Mac is full of these contradictions. It's simultaneously the most advanced and most limited computer on the market. No color, no expansion, not enough memory to run serious business applications. But it has Mac Paint, which lets you draw on the screen like it's paper. It has MacWrite, which shows documents exactly as they'll print. Wis-EYGO, they call it, what you see is what you get. Revolutionary in an era where most word processors show formatting codes instead of formatted text. Jobs gathers everyone for a demonstration. The Mac boots up, plays its startup chime, a major chord that sounds like the future arriving. The screen shows a smiling Mac icon, then the desktop appears. Jobs opens Mac Paint, draws a terrible picture of a house, prints it on the image writer printer. The room applauds like he's just walked on water. This is going to change everything, Jobs announces, and he's right, just not in the way he thinks. The Mac will initially fail, too expensive and too limited, but its ideas will infect the entire industry. Windows, icons, mouse, pointer, WIMP interface. The nerds call it, every computer will eventually work this way. Comment below if you remember using your first graphical interface and how magical it felt compared to command lines. It's 1990. You're in a data center somewhere in Virginia. The roar of cooling fans is deafening, like standing inside a jet engine made of white noise. Rows upon rows of servers stretch into the distance, each one a pizza box of computing power stacked on its siblings. The air is Arctic cold and desert dry. Your lips crack just from breathing. This is where the internet lives, though nobody calls it that yet. It's still ARPANET to the old-timers, NSFNet to the academics. The World Wide Web won't be invented for another year. Right now, it's just computers talking to other computers in a language of packets and protocols. A network engineer named Sarah shows you around. She has to shout over the fans. Each of these servers is running Unix. She yells. They're routing packets between networks, converting protocols, maintaining the backbone of what's about to become the information superhighway. She pulls you into a quieter monitoring room, screens everywhere showing network traffic, blinking lights representing data flowing between continents. It's hypnotic, like watching the neurons of a global brain firing. This is TCP/IP in action, she explains. Every piece of data gets broken into packets, labeled with source and destination addresses, and sent on its way. The packets might take different routes, arrive out of order, some might get lost, but TCP puts them back together at the destination. It's like mailing a book one page at a time, and trusting the recipient to reassemble it. The redundancy is beautiful. If one server fails, traffic routes around it. If a cable gets cut, packets find another path. The internet is designed to survive nuclear war, though right now it's mostly used for sending email and arguing about Star Trek. Sarah shows you a router, a specialized computer that does nothing but direct traffic. Inside, it's running algorithms that would make your head spin. Dijkstra's shortest path. BGP for border routing, OSPF for internal networks. It's making millions of routing decisions per second, each one calculated to find the optimal path through the network. The fascinating part is that no single entity controls this. Different organizations own different pieces, but they all agree to pass each other's packets. It's cooperation through protocol, civilization through standards. Imagine if roads worked this way, with every driveway owner agreeing to let anyone drive through their property to reach their destination. A younger technician wheels in a new server. This one's different. Instead of one powerful processor, it has multiple cheaper ones working in parallel. This is the future, he says. Why have one brain when you can have 8? The server is running a load balancer, distributing incoming requests across multiple machines. It's like having 8 cashiers instead of one really fast one. More points of failure, but also more resilience. One processor dies, the others keep working. It's biological, almost. Like how your body has 2 kidneys, 2 lungs. Redundancy is survival. Sarah pulls up a traffic analysis. You can see patterns. Business hours on the East Coast, the traffic swells. Lunchtime in California, another surge. It's like watching the planet breathe through data. Most of this is email and file transfers. FTP, Gopher, Telnet, text-based protocols for a text-based internet. Images are rare, videos are science fiction. A single photo takes minutes to download over a dial-up connection. Your phone streams 4K video without you even thinking about it. But in 1990, sending a megabyte feels like moving a mountain. The data center itself is a marvel of infrastructure. Backup generators that can run for days. Redundant cooling systems, because heat is the enemy of computation. Fire suppression systems that use special gas instead of water, because water and electronics don't mix. Every cable is labeled, documented, traced. There are maps of the cable runs that look like subway systems designed by spiders. One misplaced cable could take down entire sections of the network. The technicians treat each wire with the respect usually reserved for explosive devices. Sarah shows you the peering point, where different networks connect. It's literally a room full of cables, each one representing an agreement between organizations. We'll carry your traffic if you carry ours. These handshake agreements are what makes the internet possible. It's democracy through Ethernet cables. A crisis hits while you're there. Suddenly alerts start flooding the monitoring stations. A backbone router in Chicago has failed. Traffic is backing up like a highway accident during rush hour. Packets are being dropped, connections timing out. Sarah and her team spring into action. They're not fixing the router. That's Chicago's problem. They're rerouting traffic around the failure. Updating routing tables, adjusting priorities, basically performing heart surgery on the internet while it's still beating. Within minutes, they've stabilized the situation. Traffic is flowing again, just taking slightly longer routes. Users might notice a few extra milliseconds of latency, but their cat pictures will still load. This is the internet's superpower, resilience through redundancy. One of the senior engineers, an old-timer who's been here since the ARPANET days, comes over. "You want to know the real magic?" he asks. "It's not the technology, it's the agreement. Everyone agrees to use the same protocols. TCP/IP doesn't care if you're running Unix, Windows, or something you built in your garage. As long as you speak the protocol, you're part of the network." He shows you a network map from 1969, when ARPANET started. 4 nodes. UCLA, Stanford, UCSB, and the University of Utah. That was the entire network. Now look at this. He pulls up a current map. It looks like someone threw spaghetti at a globe. Millions of nodes, billions of connections. And it all works because everyone agreed on how packets should be formatted. It's the most successful committee decision in human history. The data center is expanding. Construction workers are installing new racks, running new fiber optic cables. Each cable can carry terabits of data, more than the entire ARPANET could handle in a year. But the principles remain the same. Break data into packets, address them, send them on their way, trust the network to deliver them. As you leave, Sarah mentions something called HTTP that some guy at CERN is working on. It's supposed to make sharing documents easier. She shrugs. Probably just another protocol that'll be obsolete in 5 years. You want to tell her that HTTP will become the foundation of human communication, that entire economies will be built on it, that people will use it to overthrow governments and share memes. But you don't. She wouldn't believe you anyway. Right now, the internet is just computers talking to computers. The idea that your grandmother would use it to video chat with relatives across the world, that's still science fiction. Hit that like button if you remember the sound of a dial-up modem connecting. That screech of digital handshaking was the sound of the future arriving, one packet at a time. It's 2007. You're standing in the Moscone Center in San Francisco. The air is thick with anticipation and body odor from tech journalists who've been camping outside since 3 a.m. Steve Jobs is about to walk on stage and change the world again, though nobody knows it yet. You're in the audience, surrounded by people clutching their Blackberries and Palm Pilots like religious artifacts. They have no idea they're about to witness their own obsolescence. The lights dim. Jobs walks out in his signature black turtleneck and jeans, looking like a tech priest about to deliver a sermon. Today he begins. We're introducing 3 revolutionary products: a widescreen iPod with touch controls, a revolutionary mobile phone, and an internet communications device. The crowd goes wild at each announcement. Then he pauses, that signature Jobs smirk spreading across his face. An iPod, a phone, and an internet communicator. An iPod, a phone. Are you getting it? These are not 3 separate devices. This is one device. And we are calling it iPhone. The audience loses their minds. But they don't really understand yet. They think it's just a better phone. They don't realize Jobs is holding the future of computing in his hand. A computer that knows where it is, can see, can hear, can feel your touch. A computer that's always connected, always with you, always ready. He slides to unlock. That simple gesture will be performed billions of times a day within a few years. The interface is all direct manipulation. No stylus, no keyboard, just your finger touching what you want. It seems obvious now, but in 2007, it's magic. The technology behind it is insane. The touchscreen uses capacitive sensing, measuring tiny changes in electrical fields when your finger approaches. The processor, a 412 MHz ARM chip, is running a stripped-down version of Mac OS X. A full Unix operating system in your pocket. The engineering challenges were staggering. How do you make a touchscreen that works with fingers but ignores your face during a call? How do you fit a useful battery in something this thin? How do you make radios for cellular, Wi-Fi and Bluetooth that don't interfere with each other in such a small space? After the keynote, you get to hold one. It's heavier than you expect, denser. The glass front is pristine, almost liquid looking. The metal back feels expensive, cold, precise. This isn't a phone, it's jewelry that happens to make calls. You open the web browser. It's showing the actual New York Times website, not some stripped-down mobile version. You can pinch to zoom, seeing the whole page, or reading individual articles. The text reflows as you zoom. It's so responsive it feels like you're physically manipulating the web page. The accelerometer kicks in when you rotate the phone. The screen orientation flips, and everything rearranges itself. It's such a simple thing, but it feels like magic. The phone knows how you're holding it and adapts. It's the first computer that's truly aware of its physical context. An Apple engineer standing nearby explains the touch rejection algorithms. The screen is actually sensing multiple touches simultaneously, analyzing them in real time to figure out which ones are intentional. When you're typing, it ignores your palm resting on the screen. When you're on a call, it turns off the screen when it detects your face. It's constantly guessing what you're trying to do, and it's right so often that you don't notice when it's guessing. The virtual keyboard is controversial. Everyone's used to physical buttons they can feel, but Jobs insisted no buttons. The screen is the interface. The keyboard appears when you need it, disappears when you don't. It frees the screen to become anything: a keyboard, a number pad, a canvas, a game controller. The predictive text is learning from you as you type. It's building a model of your writing style, your common words, your probable next words. It's literally getting smarter the more you use it. Within a few years, these phones will know how you write better than you do. But the real revolution isn't the hardware or even the interface. It's the App Store that will launch next year. Jobs doesn't mention it in this keynote, might not even have fully decided on it yet. But when developers can write apps that run on a computer in everyone's pocket, everything changes. The iPhone's processor is fascinating. It's based on ARM architecture, originally designed in Britain for low-power applications. Unlike Intel's x86 chips that powered PCs through brute force and power consumption, ARM chips are all about efficiency. Do more with less energy. This philosophy comes from ARM's origins in the 1980s, designing chips for battery-powered devices when batteries were terrible. They had to be efficient or nothing would work. Now that efficiency is enabling a computer that can run all day on a battery smaller than a pack of gum, the system-on-chip design is revolutionary. Instead of separate chips for processing, graphics, and communication, everything's integrated into one piece of silicon. The CPU, GPU, memory controller, image processor, and radio controllers are all on the same chip, talking to each other at the speed of light over microscopic distances. This integration is what makes the iPhone possible. Separate chips would use too much power, generate too much heat, take up too much space. By putting everything on one chip, Apple created a computer that fits in your pocket without burning a hole through it. The software stack is equally impressive. At the bottom, the Darwin kernel, the same Unix-based foundation as Mac OS X. On top of that, frameworks for graphics, audio, networking, then the Cocoa Touch layer, handling all the touch interactions. Finally, the apps themselves, running in sandboxed environments for security. Each app thinks it has the phone to itself, but the operating system is constantly juggling resources, suspending apps in the background, managing memory, keeping everything responsive. It's like a circus performer juggling while riding a unicycle, except the juggling is happening a billion times per second. The radio engineering alone is a masterpiece. The phone has to maintain connections to cell towers while you're moving at highway speeds, switching between towers without dropping calls. It's tracking GPS satellites, connecting to Wi-Fi networks, and talking to Bluetooth devices, all while not draining the battery in an hour. The original iPhone doesn't have 3G, just EDG data, which is painfully slow by today's standards. But it doesn't matter. The idea of having the real internet in your pocket, even slowly, is revolutionary. People will sit and wait for pages to load just for the novelty of browsing the web on their phone. Within 18 months, the iPhone 3G will arrive with faster data and the App Store. That's when everything really explodes. Suddenly, anyone can write software for the most personal computer ever created. A computer that knows where you are, can capture your world through its camera, can connect you to anyone, anywhere, anytime. Comment below what your first smartphone was and what app you couldn't live without. I bet half of you will say Angry Birds or Doodle Jump. It's 2024. You're standing in a data center again, but this one's different. The servers don't look like pizza boxes anymore. They're massive rectangles, each one containing multiple GPUs, graphics processing units, repurposed for artificial intelligence. The heat coming off them is incredible. The cooling system sounds like a hurricane. This is where ChatGPT lives, where Midjourney dreams, where the future is being computed one matrix multiplication at a time. A machine learning engineer named Alex shows you around. Each of these GPUs has thousands of cores. They explain, not like CPU cores. These are simpler, designed to do the same operation on massive amounts of data simultaneously, perfect for the linear algebra that powers neural networks. They pull up a visualization of a neural network training. It looks like a cosmic web, millions of connections strengthening and weakening as the network learns. This is essentially what your brain does, but in silicon, we're teaching sand to think by showing it millions of examples. The scale is incomprehensible. The large language models have hundreds of billions of parameters. Each parameter is a number, adjusted through training, encoding some tiny piece of knowledge about the world. The network that powers ChatGPT has learned patterns from essentially all the text on the internet. It's read every book, every article, every Reddit comment. It doesn't understand them, not like you do, but it knows the patterns, the statistical relationships between words. When you ask it a question, it's not retrieving information like a database. It's generating a response based on patterns it learned, predicting what words should come next, given what came before. It's hallucinating answers that happen to be correct most of the time. The computational requirements are staggering. Training a large model uses as much electricity as a small city. The GPUs run for weeks, months, gradually adjusting those billions of parameters to better predict the next word in a sequence. It's the most expensive autodidact in history. Alex shows you the actual hardware. These aren't normal GPUs that gamers use. These are specialized AI accelerators designed specifically for the matrix operations that neural networks require. Each one costs as much as a luxury car and uses as much power as a house. The memory bandwidth is insane. These chips need to shuffle terabytes of data per second. The connections between the GPU and memory are wider than highways, with data screaming through at speeds that make your home internet look like a dripping faucet. But the real innovation isn't the hardware. It's the architecture of the neural networks themselves. Transformers, the architecture behind ChatGPT, revolutionized natural language processing. Instead of processing text sequentially, they process it all at once, understanding context and relationships across entire documents. The attention mechanism is key. It lets the network focus on relevant parts of the input when generating each word. When it's answering a question about Paris, it's paying attention to all the Paris-related information it learned during training, weighing different sources, different contexts. It's not conscious, not aware, but it's doing something that looks remarkably like thinking, processing information, finding patterns, generating novel combinations. It's intelligence without consciousness, understanding without awareness. Alex runs a demonstration. They prompt an image generation model with a description of a scene that's never existed. Within seconds, the model has generated a photorealistic image. It's created something new from patterns. It learned like a dream machine, converting text to pixels. This is possible because the network learned the statistical relationships between words and images from millions of examples. It knows that sky is usually blue, is usually up, It knows faces have two eyes, a nose, a mouth in specific arrangements. It's learned the patterns of reality and can now recombine them in novel ways. The implications are staggering. These models can write code, compose music, diagnose diseases, translate languages, all by pattern matching at a scale beyond human comprehension. They're not perfect. They make mistakes, hallucinate facts, perpetuate biases from their training data, but they're getting better exponentially. Moore's law might be slowing for traditional processors, but AI capabilities are doubling every few months. Models that required supercomputers 2 years ago now run on phones. The edge devices are getting smarter, not needing to phone home to data centers for every decision. Your phone's neural engine, a specialized AI processor, is doing face recognition, voice transcription, photo enhancement, all locally. The same technology that requires this massive data center is being miniaturized, optimized, embedded into everything. Your car is using neural networks to recognize stop signs. Your watch is using them to detect irregular heartbeats. Your earbuds are using them to cancel noise. AI is becoming invisible infrastructure like electricity or running water. But here's the kicker. We don't really understand how these networks work. We know the math, the architecture, the training process, but we don't know what the individual neurons are doing, how the network is representing information internally. It's like we've built a brain but can't read its thoughts. We can see it works, we can measure its performance, but the actual reasoning process is opaque. It's the ultimate black box. Information goes in, answers come out, and the bit in the middle is a mystery. The future of computing isn't faster processors or more memory. It's these learning machines, getting better at pattern recognition, at prediction, at generation. They're not conscious, probably never will be, but they don't need to be. They just need to be useful, and they're becoming very, very useful. Alex shows you one final thing, a research model that's learning to control robots. It's watching videos of humans performing tasks, learning the patterns of movement, the physics of interaction. Soon it'll be able to perform those tasks itself. Physical intelligence emerging from pattern recognition. We started with switches. You realize, simple on-off decisions. And we've built our way up to machines that can learn, create, almost think, from vacuum tubes to neural networks, from room-sized calculators to pocket-sized portals to all human knowledge. The journey from E till I isn't just about making computers faster or smaller. It's about finding new ways to encode logic, to process information, to amplify human intelligence. Every breakthrough built on the last, each generation standing on the shoulders of giants made of silicon. So here we are, you're watching this on a device that would have been pure magic to the ETLI ENIAC engineers. A screen made of millions of lights, each controlled by transistors smaller than bacteria, processing power that could simulate weather patterns or render virtual worlds, connected to a global network that puts all human knowledge at your fingertips. And it all comes down to switches. Billions of them, switching billions of times per second, performing the simple magic of logic, on or off, 1 or 0, true or false, combined in patterns of such complexity that they can recognize faces, understand speech, even create art. The computer in your hand is thinking, in its own limited way, not conscious thought, but computation so complex it becomes useful, becomes almost intelligent, and we're just getting started. Quantum computers are exploring superposition, processing multiple states simultaneously. Neuromorphic chips are mimicking brain architecture more directly. The future of computing might not even use electrons, but the principle remains. Logic gates, memory, processing, the eternal dance of information being transformed, stored, communicated, from Babbage's gears to quantum qubits. It's all computation, so next time you unlock your phone with your face, remember you're holding the culmination of human ingenuity. Thousands of years of mathematics, decades of engineering, billions of transistors working in perfect harmony, all to show you that video of a cat being scared by a cucumber. Beautiful, isn't it? Hit that subscribe button if you want more deep dives into the hidden complexity of everyday technology. Comment below what amazes you most about modern computers. Is it the speed, the size, or just the fact that we've somehow taught sand to think? And remember, every time you use a computer, you're participating in the greatest magic trick humanity has ever performed, making logic physical, thought tangible, intelligence artificial. Now if you'll excuse me, I need to go water cool my GPU before it burns a hole through my desk. Until next time, keep computing.